Going to continue on with Unit 3, chemical names. And more specifically, we're going to cover some other naming. Probably the last one, which will be acids, and some off organics. When it comes to naming acids, if the anion ends in IDE, we change the ending to ic and add the prefix hydro. Some of the common ones that we have here: hydrochloric acid, hydrobromic acid, hydroiodic acid. I had a former student by the name of Becky Kep. I don't believe she is Becky Kep anymore. Regardless, she came up with this method. Hydro means no O. So if you see hydro in the name of an acid, there is no oxygen involved in that acid. Hydro means no O. Now, one of the red flags for being able to identify an acid is the fact that all acids are going to start with the hydrogen. Then some might ask themselves the question, well, what about H2O? Well, water is kind of an acid, but it's also a base. Okay? So you kind of need to know that water doesn't involve in that. But a lot of the acids, like 98% of them all, are going to start with a hydrogen. That is the red flag of you're dealing with an acid. When we name them, we have to have the word acid at the end of it. And ultimately, being able to know hydro means no O is, I think, one of the best ways to remember when you have a compound that has no oxygen, starts with a hydrogen. That means it's a hydro, because you can have a hydrosulfuric acid. It's not common, but that's not the common name. And that's the other thing is, common names and other names don't always coincide. Again, we're using the systematic ones. So be aware of that. If the anion ends in ITE, meaning it's a polyatomic ion, and in being able to recognize those polyatomic ions is very, very important. If the polyatomic ion has a prefix, we do not change the prefix, as that helps us identify what we're talking about. If it ends in ITE, we change the ending to OUS. For some weird reason, I have yet to have anybody come up with a good way of saying, how do I remember that ites are OUSs? If the anion is an acid, or the polyatomic ion ends in ATE, we change the ending to ic. Now this one is a way to remember, is the only way you know if something is icky is if you ate it. The only way you know if something is icky is if you ate it. So that is kind of, there's two ways to help you a little bit. Some little sayings to say, oh, here you go. If it's ate, it's icky. If there's no O, it's hydro. Such as chloric and perchloric acid. We can't say hydro for them because there are oxygen. So there's a little bit more memorization with the acids. Again, we tend to use a couple acids throughout the year in the lab. Hydrochloric acid, nitric acid, acetic acid tend to be the big three that we tend to use the most in the laboratory. That doesn't mean that any of these other acids are not going to be found in, say, chemical reactions that we're doing. For examples, when we do Unit 4, well, chemical reactions, and then therefore any time after that. This is a chart that some students have found helpful. It is in the naming packet that I have supplied to my classes. Some find it helpful, some find it confusing. I think you have to know your acid names a little bit more to understand it. And so that's maybe the why some students don't like it. Okay, so it is a little bit maybe over cumbersome, but some things that we can see, the prefixes don't change. Okay. The root means the chlor, that usually comes from the element in itself. Hypo doesn't change, the prefixes don't change. The ites or OUSs, regardless of a prefix. The only way if you know something is icky is if you ate it. And hydro indicates that there are no oxygen present, as it says there. This chart also goes from the maximum number of oxygen for the example one, and that is the chlorine-based polyatomic ions, and then the chlorine-based acid and hydrochloric acid. So going through and naming these in a systematic manner. Okay, the fact that we just talked about, hey, we're naming acids, that's going to help. So in the first example, because there are no oxygen, it gets the prefix of hydro. And then because it's sulfur, sulfuric, which is different than the acid that I'm not a big super fan of, sulfuric, H2SO4. Oh, look, there it is. And we do need to have the ending acid as well. Now, when I look at my next example, I can see that I have 3 capital letters, which usually indicates that polyatomic ion. It starts with a hydrogen, indicating that I got an acid. So I need to look or have, again, you have two options: memorize your polyatomic ions or utilize the reference materials that I give you. I can see that PO4 comes from phosphate, and if I ate it, I know that it's icky. Phosphoric. Phosphoric acid, commonly found in Coke, Diet Coke products. It's one of the things that makes it different than Pepsi. It is also used in also the Y if you are hauling Coke or Diet Coke syrup in a large enough quantity, you actually have to have a hazardous license to carry it. You have to have that certification on your license to carry large quantities of Coke and Diet Coke syrup because of the concentration of phosphoric acid in it. It's considered a hazardous chemical, so be careful. This next example here, we have, it ends in OUS. There's no prefix, which means that, and again, it ends in acid, so I have an H. It ends in OUS, that means it comes from the polyatomic ion, ite. And if I don't know how to do this right away, I can do the crisscross method, same as before. To give me H3PO3. Because sometimes that's where it comes, is where did that 3 on hydrogen come from? Well, it became from the phosphite because it's a -3 charge. Carbonic acid ends in ick. The only way we know something is icky is if we ate it. So we have carbonate. Charges don't match up, so we do the crisscross. To give us H2CO3. Carbonic acid. Usually formed by water and carbon dioxide. Can be as simple as just breathing into blowing bubbles into water can change the pH enough because you would be making carbonic acid through there. Now, sulfuric acid, as I mentioned before, not my favorite acid. I have been burned by it a number of times. One that has actually left scar. It's not massively large, but it hurts. Sulfuric acid in concentrated forms burns paper. It will melt plastic if you try to dissociate it in water. The whole adding acids to water method of dilution is sulfuric acid is a great example, because if you pour water onto sulfuric acid, it will spit back at you. It's pretty nasty stuff. It's also battery acid. So if you ever change a battery, a lot of times they suggest wearing safety goggles. I would highly do it. Because battery acid will burn. I mean, it eats concrete. If you have a leaky battery and you put it on the concrete floor of your garage, it will eat and etch the concrete. So something that bad is not something you want in your eye. So sulfuric acid, be very, very careful. And the last one has gotten popularity based on a TV show that made chemists awesome, and that's hydrofluoric acid. Now it says the term hydro, meaning there is no O. Fluoric means it comes from just the F. Because it's hydro and there's no O and it's an acid, it has to start with an H. And it's hydrofluoric acid. Made popular by the TV show Breaking Bad. And they said it would decompose bodies for them. It is not. It is actually used in etching of glass, and so you can't actually store hydrofluoric acid in glass because it's actually used in etching of glass. So like any glass that has some decorative etching in it, sometimes is done using a hydrofluoric paste, low concentrations. So not everything you see on TV, such as in Breaking Bad and the dissolving of bodies using hydrofluoric acid, is true. So, sorry, movie magic. Now for a little organic chemistry. When I say a little, I mean very little. Organic chemistry is considered to be the study of carbon, and when we say carbon, there are a lot of carbon-based compounds. Organic chemistry has its own system of nomenclature. We could spend probably 3 weeks covering the naming, and we wouldn't cover it all. So we are only going to give you kind of some of the basics of it. As you can see on screen, methane, ethane, and propane are common ones that you have. Why do we worry about this? Well, methane is also known as natural gas. Many people heat their houses with that. And it has the formula of CH4. We see it with the C with a bunch of H's around it. That's the structure of what it looks like. We'll get into the why the bonds are the way that is in the next unit. Ethane has the formula C2H6 for it. Ethane allows some variations of that, such as adding what's called an alcohol group. We'll look at that in, I think, the next slide. Allows for what's called ethanol, which is in a lot of our gasoline. And the last one on the screen, propane. Well, some of you, if you're not using natural gas, you might use propane to heat your house. And propane has the formula C3H8. Propane is also used very frequently for grilling, not barbecuing. Barbecuing uses cellulose or wood and or charcoal. Grilling is more of that using of propane. The simplest hydrocarbons are called the anes. And why are they called the alkanes? Because they contain only carbon and hydrogen, and they end in A and E. So all alkanes, A and E's, have only carbon and hydrogen involved with them. It's the ending of the organics that tell us some more of the story. There's even more, they get to be more and more elaborate, as that some can become cyclic, some can become very branched to the point that we have to indicate where branches are located off of them. And like I said, organic chemistry can be, the naming with it, we could look at just organic chemistry naming and for 3 weeks, and we probably would have only started to scratch the surface. So we do need to know, or should know, the formulas for these three, such as methane, ethane, and propane, because they are very common in our everyday lives. Methane, natural gas, is very common. Propane, also very common. So being able to recognize that you have this carbon-based compound with only hydrogen is extremely important. And that's going to help you out in some of the later naming packets. The first part of the name actually indicates how many of the carbons there are. Because like I said, organic chemistry has their own system of naming. In covalent naming, we would say one would be mono, but in organic naming, one carbon is for meth. And some people are like, does that mean meth? Well, methamphetamines, there is some of the naming within that, yes. There is a carbon, but it's also a mean, not that it's like, makes fun of people and stuff like it's actually mean. Amines are another method of naming nitrogens that are branched off in these organics. So, like I said, they have their own naming. Eth for 2, prop for 3. These are just some of the organics that namings that they have. There are much larger ones. Let's see if you were paying attention. Compounds composed of only carbon and hydrogen are called what? So for the slides, hydrocarbons and alkanes, both of them are correct. End of Unit 3, naming.